So we're continuing talking about counting techniques, and we looked at permutations previously, where order is important. So think back to the horse example. We cared about who was first, we cared about who was second, we cared about who was third, because those things have meaning. If they have meaning, that means it's important, or at least the order is important. So now we're going to look at combinations where order is not important. And it's very similar to permutations, even the formula. But it's important to understand that this is where order is not important. So let's just start off with the definition. A combination is given by this following formula. And you're going to notice it's very similar to the permutation except for one minor thing. So instead of a P, we have a C, permutation versus combination. There's one difference in the formula here. So the top stays the same, but on the bottom, if you recall, and just watch me for a second, if you recall, the bottom for a permutation was n minus r factorial. But now we're going to multiply something else on the bottom here. We're going to take r factorial and multiply it on the bottom. That's the difference between permutation and a combination. And we'll get to exactly what that's doing here in a minute. So we have 3 bullet points again, and they're the same ones except for the third bullet point. N is number of distinct objects. R is number of objects chosen. And the third one, most important, this is the difference between combination and permutation. Order is not important. Not. So let's jump straight into an example and see what we're talking about here. I'm going to call this example 5, just as a continuation from the previous video. So we have 4 people: Roger, Ken, Tom, and Jay are playing golf. They will randomly select teams of 2 players. So let's do 2 things here. Let's do part A. List all possible combinations. So here, this is what we've done in the past. I just want to write them out, and then in a minute we'll get to the formula. So here we can have Roger can play with Ken. Roger can play with Tom, and Roger can play with Jay. And then Ken can play with Tom, Ken with Jay, and then we can have Tom with Jay. So those are our 6 options here. These are the only possible combinations for the teams to play. So now what I want to look at is part B. Use the combination formula. So up here, I guess I should have wrote 6 and circle it. So now we have, write the formula, NCR, which is, in this case, 6 choose 2. And that's how you'll typically hear me say it from now on, is 6 choose 2. All right? And now let's just plug this in the formula. So we have 6 factorial divided by 2 factorial, and then 6 minus 2 factorial. Keep simplifying here. We get 6 factorial on the top, divided by 2 factorial, and then that's times 6 minus 2 is 4 factorial. All right, there's a couple ways you can go about, oh, and I messed up. So let's, this is supposed to be a 4. So let's mark that out. That is my fault, sorry. Start over. And now this is 4 choose 2, because we have 4 players and we're choosing teams of 2. Now that's equal to 4 factorial all over 2 factorial, and then 4 minus 2 factorial. Simplifying here, we get 4 factorial over 2 factorial, and then 4 minus 2 is 2 factorial. Now, if we were to, there's a couple different ways we could go about doing this. On the top, you get 4 times 3 times 2 times 1. And on the bottom, 2 factorial is 2. 2 factorial is 2, so you get 2 times 2 on the bottom. That equals 12 on the top divided by 4. Oh, excuse me, 24 on the top. Right. 24 on the top divided by 4, which is 6, which is what we were expecting, and that's good to see. So what if we accidentally use the permutation formula here? That's what I want to look at. We can see that these A and B line up, but what happens if we were to do a part C here? Part C, use permutation. Here, what we would get would be in PR, and then, and here I want to preface this as wrong way to work this, just so you remember in your notes that this is not the right way to do it. But I want to show you what the meaning is here. So we have 4p2, and then let's write our formula. 4 factorial all over 4 minus 2 factorial. So we get 4 factorial divided by 2 factorial. Simplifying this, you get 24 on the top, 2 on the bottom, and that equals 12. So what is this telling me here? So what this is doing is the permutation takes into account the reverse order of each of these. So here, when I'm dealing with the permutation, it sees Roger and Ken as one possible combination, and it sees the reverse, Ken and Roger, as another possible combination. And then here it sees Roger and Tom as another combination, but then it also sees Tom and Roger as another combination. So it does that for every single one of these, so that's why it's 12. But to us, and what we care about, we don't care what order it's in. We don't care if Roger was picked and then Ken was picked, or Ken was picked and then Roger. So that's why we use combinations in this case. Now, if we were dealing with a horse race, we would not want to use a combination because order is important. So if order is not important, we use combination, because we don't care if Roger or Ken was picked first in this case for this team. We don't care if Ken or Jay was picked first for this combination. So that's that there. Let's look at another example, and we'll call this example 6. how many 5-card poker hands can be drawn from a 52 deck of cards. Assuming it's a fair deck and everything is lined up the way it should go. So here, we would want to do 50. Well, let's first write our formula. It's N choose R, so we're dealing with combination here because order is not important. So what I mean by order is not important, let's just say that, I'm just making up an example here. Let's say that you drew the cards 2, 3, 4, 5, and 6 in that order. All right, and that's a heck of that's a good hand in poker. So that's one option there. But let's say instead you could have drawn this 3, 2, 4, 5, 6. So the only difference is these two flipped. All right. Permutation would count both of these, whereas a combination will not. So here, and we could keep going with this. We could do a third option, and we could say 2, 3, 5, 4, 6. So that is a permutation would count this also. As long as it's the same 5 cards, we could have many different possibilities here. So a permutation will count, I don't know how many this is exactly, 120 possible combinations, whereas a permutation will account for 120 possible ways to draw these 5 cards, whereas a combination will take all those 120 and just boil it down to 1. So a permutation would count all of these. A combination only counts it once. And that's what we want here, because we don't care what order we get the cards in, they still always give you the same hand no matter what. Now if this was a horse race, of course we care which one would get, who would get first and who would get second and so on. So that's why we're using a combination here. So it's 52 choose 5, which is 52 factorial divided by 5 factorial, and then it's 52 minus 5 factorial, which is equal to 52 factorial over 5 factorial times 48 factorial. So doing this a little shorthand here, I have 52 factorial and a 48 factorial. So I know this 48 factorial will cancel out all from 48, 47, 46, and so on. So on the top, all I'll be left with is 52, 51, 50, and 49. So, and then this would get canceled out, and I'm left with 5 factorial on the bottom. And you simplify this, and you get 54,145. All right, so if this is a little confusing to you, go ahead and write it out and see if you see what I did here. It will be a little helpful in the future to know how to start doing some of these shorthand. And that's it for now.